All right. It is barely the third week of school, and it's time to learn calculus for your Physics C class. In Physics 1, one of the big ideas that we spent a lot of time on was talking about like the slope of certain graphs, particularly your kinematic graphs, and the area of the graphs. And we worked with pretty simple functions in Physics 1. Okay, now it's time to step it up a little bit. We're going to start looking at objects that don't move with a constant acceleration. They've got some weird acceleration function, and we're supposed to figure stuff out based on these new values. So the slope, right, super duper important. The slope of a position versus time graph is velocity. The slope of a velocity versus time graph is acceleration. And there's a whole bunch more functions that we deal with where we look at the slope and we look at the area. So if you need to find the slope of a function, you need to take the derivative. So you have a function, let's say a function f of x, it's got blah, blah, blah. There's an x in there somewhere as your independent variable, okay? To indicate that you are going to take the derivative, there's several different notations, all of which are fine. And you would verbally say, I'm going to take the derivative of the function with respect to x. We are going to be primarily dealing with our kinematics equations, so we will be dealing a lot with derivatives with respect to time rather than position. So there is one super important, this is like the most common derivative that we take, and it's called power rule. This works for polynomials, okay? So if you have a function that's like ax to the nth power, when you take the derivative of it, first you multiply your exponent by your coefficient. Okay, that becomes your new coefficient that you just stick up in front. Okay, then you leave your the variable that you are deriving with respect to. So you keep it there, right? It's still an x. It hasn't like transformed or anything. But you're going to subtract 1. You're going to knock that exponent down by 1, which gives us our solution. So let's take, our very familiar, I hope, position versus time graph, position versus time equation. X equals 1/2 at squared plus v naught times t plus the initial position. So I want to take the derivative of this. And hopefully from your first physics class, okay, the slope of a position is velocity. So I'm going to derive the velocity equation from this position function. So let's make this a little more colorful. Okay, time is our variable that we are deriving with respect to. Okay, our exponents, I've added a couple in case they weren't obvious. And then we're just going to go with it. Okay, so you'd say dx dt is equal to v. Yeah, that makes sense. And then it's equal to, okay, well, you take your exponent, you multiply by 1/2, your exponent decreases, da 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 da. Okay, so this is what it looks like unsimplified. And we can clean that up a little bit. We can take care of our fractions. We can get rid of the stuff that's equal to 1 or equal to 0. And, beautiful. It is our velocity as a function of time equation. So finding the slope of a function is a derivative. We also go backwards, right? We talk about finding the area underneath a function a lot, and that's very closely related. It's essentially a derivative backwards. So this mathematical process is called an integral. The slightly complicated thing about integrals is that when you're finding the area underneath let's say a velocity versus time graph, okay, you don't get a position function out of it. You get the displacement, as in like the change in position function out of it, but you don't necessarily know exactly what that object's position is unless you know where it started. Okay, so when you are integrating, you got to throw in this extra constant, this like plus c at the end in order to take that into account. But the notation is pretty similar. We've got kind of like a swirly upright S. And the verbiage is pretty much identical. You say, I'm going to take the integral of this function with respect to x. So if I'm literally just trying to undo the derivative, I'm literally going to undo the steps. So the very, very last step in the derivative is knocking 1 off of the exponent. Here I'm going to start by adding 1 to the exponent. Then, with that new exponent, I'm going to take my coefficient and divide it by that new exponent. And then the third step, you got to stick that plus c on the end, or if you know like exactly over what bounds you're integrating, you're going to have to evaluate that integral like numerically. More on that later. So here are the steps again. Let me skip forward a little bit. Here is the general form, since I didn't have room for it on that last slide. We will essentially just take the same function that we just worked with and go backwards for simplicity's sake. Y'all are already familiar with this particular kinematic equation. You kind of know what the outcome should be. So we're looking at the v is equal to at plus v naught equation. Okay. We know that another way of writing velocity, it's the derivative of position with respect to time. Yeah, fancy, right? So that's that dx over dt thing over there. And don't tell your math teacher this, but you can kind of treat that differential operator, that d over dt thing, kind of looks like a fraction, right? You can kind of move that dt like over to the other side, so that you're just left with dx over here on the left. It's not like you're multiplying, but it kind of looks the same. Okay, the process is very fancy, very technical. We don't really super care about it as physicists. It works, right? And that's just kind of what we're trying to get through. So dx is equal to at plus v naught, and then I bring that dt over. It's like I've multiplied it on both sides, but it's not multiplication, it's differentiating, I guess. So you stick the dt way out on the right side, and technically this dt applies to everything, like that whole entire right side of the equal sign. Okay, it's like the distributive property, but like not, because it's not multiplication. Just go with it. So now that you have this, we slap our integral signs. We just kind of like sneak them in right there, because what you do unto one side, you must do unto the other, right? That's like the golden rule. Since an integral is the opposite of a derivative, that swirly upright s kind of cancels out with the d in the dx. And then we are left with, oh, I went ahead and did it. I got excited. We are left with x is equal to, okay, the integral of this function. And so we kind of go through the process, right? Because we've got a times t for the first term. We kick the exponent on t up from a 1 to a 2. And then we divide our acceleration by 2. For the next term, oh, it looks like just a v naught. Where did this t come from? There's a secret stealthy t to the 0th power lurking by the v naught, because like anything to the 0th power is 1, so it's fine. All right, so it's v naught times t to the 0th. Well, you kick the 0 up to a 1, and oh, suddenly you have v naught times t. Technically, it's v naught divided by 1 times t, which is just v naught. So that's how we get that second term. And then last but not least, because we're trying to write a position function and we don't know what the initial position is, we got to stick this plus c, or perhaps should I say plus initial position on as our constant of integration there at the end. So we've pretty much just gone backwards from our last derivative example to derive the position function once more.